Hi again. So I welcome everyone to the fourth lecture of the seminar in computer architecture. So today I'm going to discuss one of the key topics in computer architecture, which is virtual memory. I have been working on this throughout my PhD. So the title of my talk is on how we can rethink the hardware and operating systems interface so that we can enable more efficient memory management. Who am I? I'm a PhD student working with Professor Onur Mutlu, the Safari Research Group. I wrapped up my undergraduate studies in the National Technical University of Athens, and I'm very interested in hardware OS and software co-design with a focus on memory management. And recently we explored also some directions along the lines of microarchitecture and DRAM security. You can find more about me on the website. So let's talk right now on the interesting parts of the presentation. This is the hardware OS and software cooperation, which is in the foreground here. So we have the operating systems on the higher levels of the stack. We have software below the operating system, and we also have the lower levels of the stack where hardware lives. And you can think of virtual memory as some sort of abstraction that lives between all these layers. On the operating system side, we are managing memory. And we are generating program addresses through the programs. And these program addresses go through somehow through the abstraction of virtual memory, and the hardware translates them, and we can eventually access the physical device. So we have been doing some work in this direction. We designed the simulation infrastructure for hardware and operating system synergistic schemes called Virtuoso, which was published in ASPLUS 2025. One of you is going to present it, but I'm going to give a preliminary presentation first. We also published two works on how we can accelerate the process of address translation at the hardware and OS level. And we also proposed another work where we simply focused on the hardware part of how we can translate quickly virtual to physical addresses. The first part of my talk is Virtuoso, which is our latest work. And it's about how we can enable fast and accurate virtual memory research with an imitation-based operating system simulation methodology published at ASPLUS 2025. The code is open source, and I'm going to talk to you about later about the workshop that we're going to do at Micro 2025 about it. So I'm going to dive into some basics because I'm not sure how is your background on virtual memory. How many of you had a course or something related compared to virtual memory, like that embedded some concepts of virtual memory in it? Okay, that's a good amount, I guess. So it's a technique informatique probably that you had, or some, like which course did you take that involved concepts of virtual memory? Oh, SPC, yeah, that's also okay, yes. Any other one?
Yeah, digital design.
Oh, digital design also, yeah, okay, sure. That's nice. So let's see what benefits does virtual memory bring into the game. First, we can have programmer transparent memory management. When you write your programs, you do not need to write taking into account the physical memory that lives inside your system. You just express stuff using virtual addresses. All the operations you're doing in Python, C, C++, everything is working on virtual addresses, not on physical ones, which is very nice because you do not need to change your piece of code every time the hardware changes. Second, we can isolate processes. Back in the days, if we had systems like some older Cray supercomputers, we were using only physical addresses. And what is the problem with this? If I wanted to port two applications written by two different people, I would need to somehow make sure that they would isolate and nobody would touch the data of another one. So with virtual memory, this is ameliorated, and we can isolate processes a lot more naturally. And third, we can share data between processes. If we abstract away the concept of physical memory, then we can make the virtual addresses of two different processes point to the same data in the physical memory. And this way we avoid duplicating data. The question is, okay, these benefits are very nice, but how does that work? So let's have an example. Here we have two applications, app1 and app2. And each one of these applications has its own virtual address space. So this is the physical address space, the physical memory, for example, the RAM you have in your systems, right? And we split both the virtual and the physical address space in chunks, which we call pages. And in most of your systems, the page has a size of 4 kilobytes or 16 kilobytes. For example, most recent Intel processors have 4 kilobytes. MacBook Pros have 16 kilobytes of base page size. How do we make virtual addresses point to the physical address space? So when you touch your data, you need to somehow install it from the virtual address space and make it point somewhere in the location in the physical address space. And this is happening via the virtual to physical address mapping. So you can think of it as a directory where we essentially store information about where is this virtual address stored inside the physical address space. And the question right now is, okay, this address mapping is useful, but who establishes it? Who creates the mapping between the virtual addresses and the physical addresses? So again, you have an application here and it has its own virtual address space, right? And you can see this page on the left, and you can see the physical memory. And at some point in time, the virtual address on the top that is chunked, we need to map it somehow to the physical memory. But the question is, who does that? We have a fault because the mapping is not established and no one has established it till now. So someone needs to map this virtual address to the physical memory. And the operating system takes over in modern systems. So the operating system handles the memory allocation and establishes the mapping for us. We stop the application because the mapping is not established yet. And the operating system, the first thing it tries to do is find free space in the physical memory to place our data, our virtual page. This is called the minor fault, and you might have seen it in previous lectures on operating systems. If, though, the data needs to be fetched from the disk, for example, you want to read the file using your program, right? This is a file-backed data, and it's not stored already in memory. It's somewhere in the disk. Then you first need to fetch it from the disk, then find free physical space in the physical memory, and that's what we call a major page fault. And as you can imagine, it's a lot more expensive to have major page faults compared to minor page faults. In major page faults, we need to fetch data from the disk, which makes it a lot more expensive than simply trying to find free space in the physical memory. Any questions? No. Okay. So once the operating system does this, then it somehow needs to store or update the virtual to physical address mapping. And this is done through the page table. The page table is a data structure that lives inside the memory. So when the operating system is done with allocating memory, it goes and updates the page table who also lives inside the memory. And the question is, okay, we have the page table right now. The OS did its job by updating, inserting the mapping. The question is, how does the hardware will figure out when it wants to load the virtual address, what is the actual physical address that is stored in the physical memory? Through the process of address translation. What does the process look like? The core, when it needs to access a specific virtual address, it ships a packet to the memory management unit. And the memory management unit is a hardware component which is responsible for one thing: taking a virtual address, giving back the physical address on runtime while the program is running. How does it do that? It needs to somehow load the page table from the memory hierarchy, do some magic, as I will show later, and do this very fast. So because this happens for every virtual address needs to be translated to a physical one in I think, all modern systems these days. So how does the memory management unit look like? There is a component first, a bunch of components, which we call the TLBs. This is the translation look-aside buffers. So the translation look-aside buffers store virtual to physical mappings directly. So using the virtual address, we can derive the physical address. And these are caches that store this sort of mappings. When we miss in the TLB hierarchy, then we need to find the virtual to physical mapping via accesses to the page table. And to load the page table, we need to go to the memory hierarchy. In more detail, there are two different TLBs at the L1 level. One that caches translations for instructions. So we also need to load instructions. We don't need to load just data, right? So translations are also stored within virtual addresses. And we have one TLB at the L1 level that stores translations for data. If we miss in these two TLBs, then we access a unified L2 TLB. And the unified TLB stores translations for both instructions and for data. If we miss in the unified L2 TLB, then we trigger a page table walk process. So the page table walk process simply is responsible for performing memory accesses to figure out what is the virtual to physical mapping. So it's as if we're accessing a directory and an index, a directory, and we want to find out what is the virtual to physical mapping. And you can think of this specific hardware unit as a state machine. It's a simple FSM that looks up recursively the page table. I will discuss later how exactly this happens. The page table walker also uses some hardware components to accelerate the process of figuring out the page table data. These are called page walk caches. And the page walk caches help us because the page table does not have a single level, it has multiple levels. And the page walk caches help us because we can basically skip performing memory access for some of the levels in the page table hierarchy. If we miss in the page walk caches, our only option is go and fetch the page table data from the memory hierarchy and bring it over to the memory management unit and install the translation, the final translation inside the TLBs. And there are a bunch of components like network interface cards, CPUs, GPUs that make use of this abstraction called virtual memory. As you may see in the future courses and this course, there's like virtual memory is one of the cornerstones because we always need to virtualize memory to enable spatial sharing and multi-tenancy in modern systems. However, it doesn't come for free. So it causes high performance overheads because of two things I just discussed. The first one is memory allocation. So first, when we want to install our data and establish the virtual to physical mapping, we need to pay a high price to achieve that, and I will explain why. Second, address translation. When we want to translate virtual addresses to physical addresses, then again, we need to perform a high price in terms of access the page table a lot. When it comes to memory allocation overheads, we have a bunch of emerging workloads like function as a service or serverless workloads, if you have heard about it. Or we have this short input, short output, large language model inference. Like the inference server is, you're just spamming it with queries that are very short, and they need to allocate lots of memory just for a very short amount of time. These workloads are short running. For example, we might run them in less than 1 second, each one of these queries, let's say. They also have a very high spawning throughput. We need to satisfy them at a very high throughput. And what's the problem here? We spend a lot of time on the operating system memory allocation routines. We need to spend a lot of time to allocate memory and establish the memory in the physical memory for these workloads, while the execution does not amortize the time we spend. So essentially, the time we spend in the operating system to install memory does not amortize it does not get amortized because of the very short execution time of the function or the query itself. And as I will show here, that's a big problem. Here, we saw the fraction of the total execution time of the physical memory allocation across some workloads from function as a service, matrix operations, and LLM inference. And as you can see, on average, we spend 32% of the execution time, which we measured in a real system, on physical memory allocation. So just to establish the virtual to physical mapping, we pay 32% of the execution time in these workloads. Yes, sure.
Time means time or CPU cycles?
It's the same. It's similar, right? So in this plot, we know it doesn't matter whether you normalize on CPU cycles or time. You can think of it as this analogous thing. It's the same thing, essentially. Of course, you can translate your CPU cycles to time if you know the frequency, right? Yeah, so the same exact argument could be said that like fraction of total execution cycles, if that's the question. And second, we jump to the address translation overhead. So memory allocation is expensive. We saw it for a bunch of workloads. There is another sort of emerging class of workloads like sparse machine learning workloads, bioinformatics workloads, graph analytics, databases that are a lot more long-running. For example, we have a very large database with hundreds of gigabytes, which executes many queries for a long amount of time. And these workloads have the problem of irregular memory accesses. They do not access memory in predictable patterns, basically. And this unpredictability in the irregular access patterns, in combination with the fact that the datasets are very large, cause a lot of TLB misses and page table walks. We need to go and access the page table again and again and again, which makes each memory access very expensive. So we pay a very high price and high latency in address translation before we can access our data. So before we actually go to the memory to fetch our data, we need to pay a very high amount of cycles to perform address translation. And you can see here again the fraction of the total execution time that was spent on address translation on a bunch of very large data set irregular workloads like graph analytics, some quantum simulation workloads, and some genomics ones. So if you see this plot carefully, on average, 26% of the execution time, again measured on a real system, is spent on address translation, which means it gives us a very big headroom to work with, because getting 26% back is a very good thing, basically. In compilation, we have minor page faults, which is actually the memory allocation in this context, and address translation, which cause diverse types of overheads in emerging workloads. And these sort of overheads are expected to increase as we transition to much larger physical address spaces. As you can see here, you can see a GPU memory and a CPU memory. You might have seen this a lot in data centers, for example, where you have a GPU memory with a very high bandwidth to perform very fast LLM inference, for example. But this GPU has very limited capacity. For example, a high-end H100 or A100 might have 80 gigabytes of memory. On the other hand, we have CPU memory with a very high capacity, but a lot with a very high capacity, lower cost per bit, but we cannot run our workloads there because we need the parallelism that the GPU offers, right? So there's a concept called unified virtual memory where we treat both memories as one, and we're able to transparently move our data around between these two. But having such a big memory means that the virtual address space gets larger, the physical address space gets larger, and the potential overheads of virtual memory get larger. Second, there are some proposals to directly access storage. For example, directly from our application, we can have a byte addressable interface to be able to access the high-end SSD. Again, the physical address space becomes extremely large, which means that the potential overhead of virtual memory starts becoming large because the TLBs cannot fit all this translation metadata inside the core, basically. And third, we have also the memory disaggregation. If you have seen proposals like CXL, for example, I might operate on data that live in my local memory, in my local laptop or server, but I could expand my storage to other remote memories, other remote devices, so that I can basically expand my memory capacity. Again, same problem, bigger physical address space. I cannot fit all my translations basically inside the place where I compute, where I need to translate from virtual to physical addresses. However, we have researchers who try to save the day with respect to all these overheads. And they're trying to basically co-design the hardware and the operating system to reduce all these overheads of virtual memory. There are many approaches who basically say the following: okay, these hardware TLBs are very small, and it's very costly if we want to expand them and make them double, triple, quadruple the size. So what we're going to do is we're going to use a software TLB. You can think of it as a mini page table that stores the hottest translation entries. And there are a bunch of proposals who try to propose this. And on the other hand, we have some other proposals which try to leverage virtual address to physical address contiguity. And what does this mean? If I know that a virtual segment of arbitrary size can map to a physical segment of arbitrary size, then if these two are contiguous, I can create simply a pointer-based connection between the two, like an offset. So I do not need to translate at the 4 kilobyte granularity or the 16 kilobyte. I can translate directly using an offset. And again, there's a bunch of proposals here that try to leverage this in order to accelerate address translation. Then there's another type of works which were like, okay, so we cannot afford trapping and performing exceptions through the operating system, because these context switches are very expensive when we do memory allocation. Again, let me remind you, when we want to install the virtual to physical mapping, the application needs to stop, the operating system takes over, and then the operating system says, okay, I'm done, you can continue the execution. But we waste very important cycles, a high amount of cycles to achieve this. And this works, we're like, okay, we will offload part of the memory allocation down at the hardware level, and this will accelerate fundamentally the way we allocate memory. And another bunch of works try to use alternative address mappings, and these works use different hash-based schemes to perform virtual to physical translation to avoid using the page table as a whole. I will describe the last one of them today in the second part of the lecture, so I'll keep you posted on that. And altogether, there are many, many other approaches that try to deal with the problems of virtual memory. So imagine there's a wide variety of techniques. It's like a huge tool set that aims to improve the virtual memory overheads. And if we want to progress in the domain, we need to find a way to evaluate all these very effectively. So what is the problem with evaluating these very effectively? So as a computer architect, the problem is that you need to deal with 3 different levels of abstraction. First, we have the software level management, which means that the operating system needs to run some stuff at the software level. And these pieces of code that it runs in the software level interact with the hardware MMU. Why? Because when you change the page table design, then you might affect how the TLB stores something at the core level. And it also interacts with system components. Let's say the operating system decides to migrate a page from point A to point B. What is the problem with that? Does anyone know? What's the problem if I try to migrate a page from point A to point B? Basically, there are 2 problems with that. Anyone? Okay, so the first problem is that you need to consume energy, because I move data from one place to another. Second, I spend bandwidth because I consume cycles that the DRAM is working to move my data from point A to point B. And third, I make the application wait for memory allocation while I'm migrating. So I have basically many problems when I'm allocating memory that are dealt at the system level. So the operating system causes problems at the system level. So the problem is that all these interact with each other. There's a very clear interplay between all these components, and this is very hard to capture with existing tools, as I will show you later. To give you an example, the page table and the large pages. So the page table is very much dependent on the operating system allocation policy. And let's talk about Linux here. So the size of the page table depends on the number of large pages provided by the OS. In most Linux systems, we do not just use 4 kilobyte pages. We have the option to activate 2 megabyte pages, which is a much higher number, a much larger page size. What does this mean? We can pack a lot more metadata and information in a 2 megabyte entry instead of a 4 kilobyte entry. When the operating system kernel says, okay, I can provide plenty of large pages, then what happens is the following. We can shrink the page table. We do not need to store as many mappings compared to using 4 kilobyte pages. And this is a good scenario because our page table became smaller. We can fit it much more easily inside the caches, inside the memory, and we have space free. However, in some cases and in many systems like data centers, where we have multi-tenancy and multiple users running at the same time, fragmentation is a key problem. And when fragmentation of memory is rising, then we cannot allocate easily 2 megabyte pages. And when we cannot allocate 2 megabyte pages, the operating system says, okay, I cannot provide 2 megabyte pages, I need to give you 4 kilobyte ones. And in this context, the page table needs to store a lot more entries to be able to cover the whole physical address space. And again, this is a trade-off here because we cannot provide 2 megabyte pages, and the interplay is that the page table immediately becomes larger. Another example of interference and interplay. You might have seen in the previous lectures that how a DRAM bank is organized. For example, a DRAM bank is organized with many rows and a row buffer. And in this context, the row buffer stores the most recently accessed row. In this case, application 1 occupies the first row with some page table data. So we have the page table of application 1 in the top row. Let's say that the page table is in total 4 kilobytes or 8 kilobytes in this scenario. Application number 2, running in the same system, is using some normal program data in the last row. And the most recently accessed row is applications 2's data. So we can, with lower latency, directly from the row buffer, we can access the data of application 2. So application 1 needs to access the page table. Does anyone know what this problem this would create? There will be a conflict because the most recently accessed row would become the page table entries from application 1. And this means that I need to remove the data from the row buffer from application 2, install the page table entries that exist in application 1's row, and then next time I need to access the application 2's data, I have another conflict, which means that next time I access the data of the application 2, I need to pay a higher overhead. I need to pay more cycles. And this problem stemmed from the fact that App1 used lots of page table entries, and it creates a problem to other applications. So you don't just create problems to your application, you might create problems to other applications co-running in the system with the overheads of virtual memory. Again, this interplay is challenging, and if we want to evaluate properly and assess the new and the current virtual memory techniques, we need to evaluate this interplay very effectively. And researchers have architectural simulators at their disposal to achieve this. And there are too many classes of simulators, and you will see this we use lots of these in the master's course. We use at least 4 of these in the master's course of computer architecture. And if you want to follow the direction of computer architecture, then you will for sure see a lot of these in the future. First, emulation-based, and second, full system-based. What does this mean at a very high level? They're trying to emulate the operating system, the first class, and the second class, they're basically running the operating system. So you can think of it as like a fake operating system on the top, full-blown operating system on the bottom. To give you an idea, our emulator, which is crafted by the group, Sniper, ChampSim, and many more, have a very high simulation speed. Why? Because they do not need to simulate the whole operating system. They just simulate a program, basically. They focus on different microarchitectural features like caches, prefetchers, main memory. So the problem is that they have limited support for operating system primitives. But as we discussed before, the operating system software is a key property of virtual memory, and we cannot just skip it when we simulate our techniques. And second, they typically analytically estimate virtual memory overheads, and I will explain why this happens. Second, we have full system simulators, and full system simulators like Gem5 full system, if anyone has heard of Gem5, this is also supported by ARM, for example. There is QFlex, there is PTL-Sim. What is the good thing here? So the good thing is that these simulators, they can basically emulate the full system, the full-blown operating system, and simulate it at the same time. So what's the problem with this? First, the simulation speed is a problem. The simulator becomes a lot slower when you run on top of it the whole operating system. And second, it's very hard to develop. If anyone has tried to work with Gem5 full system, for example, it's a very hard entry point, basically, for a student to jump directly into the Gem5 full system simulation mode. So as you can see, we have the following dichotomy. We have simulators which are emulation-based. They have very high simulation speed, but the accuracy in estimating virtual memory overheads is not so high. Now, at the same time, we have full system simulators, which they do take into account operating systems, but the speed is very low, and the development curve is also very low, which is not shown in this plot. So in this work, we try to bridge this dichotomy, and we try to create a simulator which is also has a high simulation speed and also achieves high accuracy in estimating the virtual memory overheads. And yeah, we call it Virtuoso. It's a simulation framework that basically enables very fast and accurate prototyping of both the software and the hardware components of virtual memory. At the core of the simulator is a concept called the imitation-based simulation methodology, which you can think of it as the following way. We have a lightweight user space kernel. Instead of using the whole Linux, for example, we developed a mini version of Linux, which is written in a high-level programming language. We wrote it in C++. And basically, our Linux, let's say, it chooses the OS modules which are related to our research. For example, this tries to imitate the full-blown operating system. And how does it do that? This is a full-blown Linux kernel, which has many of these. How I can manage non-uniform access memories. There is a thread scheduler. There are like C groups, the block device driver, the boot process, should still BFS. But we strip it away from all these things, and we kept only the ones that are related to the research that we wanted, like swapping support, transparent huge page support, handling virtual memory objects. We packed all these into a new kernel called the lightweight user space kernel called Mimic OS, and we are basically reducing the overheads in simulation while keeping a high level of accuracy in our simulations. This enables very rapid development and prototyping, high simulation speed by executing only the desired OS functionality, and accurate evaluation because we can integrate this kernel that I just described to various architectural simulators. And let me give you a very quick description of how this works. So this is a lightweight user space kernel, and let's say that we packed inside this thing the desired memory management modules. Okay, and underneath this is our simulator. Let's say SAM, SIM, emulator, our architectural simulator, the one that models physical components, basically. There is a concept called binary instrumentation, which means that I can find out on the fly what sort of instructions is the lightweight user space executing. And once I find this, I create an instruction stream. So I figure out that this is executing this addition and this load, right? And I can generate this on the fly with binary instrumentation. I feed these instructions into my architectural simulator that does one thing. It simply models the core, the memory, or whatever I want, right? And what does this offer? It offers the fact that I can imitate the operating system level overhead. If my user space kernel is doing something that's very computationally intensive, the simulator will find this out because the instruction stream will be very intensive. And what is another good thing about it? We create another channel where we can send the functional outcome down to the simulator. And this enables the emulation of kernel modules. And let me give you one quick example. If our user space kernel figures out that the best page size is 2 megabytes instead of 4 kilobytes, it can communicate this from the user space kernel down to the simulator so that the TLBs and the page table become smaller. If I could just simulate the instructions to create the 2 megabyte pages, this would not be enough. I also need to inform the simulator about the functional outcome of what I did at the simulation, at the operating system level. So you can think of, I will give you a more detailed example right now. We have two things, the transparent huge pages and the body allocator. The body allocator is responsible for finding free pages, and the transparent huge pages is responsible for finding out if body has a lot of free pages which are contiguous. We have an example simulator. This is the simulator that we use as a baseline here, and the example user space kernel. So we're running our workload. We run an application, let's say our machine learning inference, right? So we perform more memory access. We send the memory access to the simulator, to the core model of the simulator. And the core model of the simulator tries to model the MMU, basically, and the translation subsystem. And it says, okay, I do not know how to translate the virtual to the physical address. Someone needs to tell me what is the physical address so that I can send it to the memory. So we send the page fault signal at the user space kernel, and what happens is the following. We have a specialized software-based page fault handler, which gets instrumented at the binary level. It produces an instruction stream, which is sent as a feedback back to the core model while the translation is happening. And this means that at the same time, we are sending the instruction stream and the core model can basically estimate the overheads of the page fault handler, how many cycles did it take to resolve the page fault and handle virtual to physical address translation. And at the end, after this is done, we also communicate the outcome. And we're saying, okay, this page I instantiated using 2 megabytes instead of 4 kilobytes, or 4 kilobytes instead of 2 megabytes. And this way we can basically be a lot more realistic when we model the MMU and the translation subsystem. Basically, we wrote many of these modules in C++, and there are a lot more details in the paper. You can find it out. And yeah, we packed many of these here, and we're even adding more as time progresses. The good thing with this is that once someone creates this big tool set of techniques in one domain/topic, the good part is that it creates like some sort of ground for researchers to evaluate and estimate techniques with in a single way, like in a singular way, without jumping around different simulators and different configurations. So we integrated the kernel, the Virtuoso, on Gen 5 system call emulation mode, Ramulator, which comes from the group, Sniper, SAMSIM, and MQSIM, with a focus on storage devices, because lots of virtual memory studies rely on storage. We need to swap out pages in modern systems, and having a simulator for storage that connects to the user space kernel is very useful. And we validated Virtuoso integrated into Sniper against the Linux kernel running on a very high-end server-grade CPU. And what did we find out? So simulators, one of the metrics that we use to compare simulators and evaluate simulators is the IPC accuracy. So what does this mean? It means how many cycles do we spend to execute, how many instructions can we execute on a single cycle in our processor versus how many instructions does the simulator say that we can execute in a single cycle. And as you can see here, we compared the baseline Sniper without a Virtuoso, Virtuoso plus Sniper, and Gen 5 full system. The Gen 5 full system is the beast simulator. It's much slower, but very accurate. And we find out that if we integrate Virtuoso with a baseline simulator like Sniper, this improves the IPC modeling accuracy by 21% compared to the baseline one. At the same time, Virtuoso integrated with Sniper achieves IPC modeling accuracy within 9% of Gen 5 full system simulation, which means that we're closing the gap to the beast simulator, the very good simulator. What do we win, though? We lost a bit of accuracy compared to the Gen 5 full system, right? So what do we win? What we win is that Virtuoso incurs a 20% slowdown compared to existing simulators like SAMSIM, Sniper, Ramulator. But when we port it to Gen 5, we cause a 28% overhead. But once we enable the beast, Gen 5 full system, then we get a 77% overhead. So you can think of it in the following way. We lose 9% accuracy, but we get back 50% of execution time. About its versatility, so we demonstrate in the paper the versatility of Virtuoso across multiple different use cases, and we try to demonstrate new insights on state-of-the-art virtual memory techniques. We have 5 use cases in the paper, but I'm going to talk about one of them here, which is on how we can evaluate nicely physical memory allocation policies. What's our evaluation methodology? So we want to study the memory allocation overheads. Our baseline is body, which means that whenever we request a page, we need to go through the body system to retrieve information about which pages in the system are free. And our comparison point is Utopia. Utopia is the paper I'm going to talk after the break, which is about how we can organize part of the memory with restrictive hash-based mapping to accelerate allocation. So instead of searching in a body, what we do here is that we simply hash the virtual address, and we find out if the result of the hash goes to a free page or not, which makes it a lot faster, but more restrictive than body. And as workloads, we use short input, short output LLM inference. You can think of it as like we spawn a server, and we are basically having 3 different servers with 3 different models, and we're sending queries to each server. And you can think that each query consumes some memory. For example, if you know the KV cache consumes a huge part of the memory of the query's memory. And we figured out the following, that if we basically use Utopia instead of the classic body-based allocator, then we can, by restricting this mapping, we can speed up memory allocation by 2.17x compared to body. And this is something enabled by the simulation framework itself. This is something that you cannot easily do in modern systems, basically. And there are a lot more details in the paper about the communication primitives, the modules of Mimic OS, how we integrate with different simulators. There's a lot more on that. Yeah, it's open source. Like one of the labs in the last FOCA course was on Virtuoso. And one of them would be also in the computer architecture one, I think lab 6 would be. There's a website with documentation. And yes, if you would like to, there's a workshop which we're organizing at Micro 2025 on Virtuoso. Do not ping me if you want to give a talk. Just come and listen, or probably you will find it on YouTube available. So we will do a live demo with the other Constantinos. And in conclusion, virtual memory causes very high overheads in emerging workloads. We presented Virtuoso, a new simulation framework to prototype both the hardware and the software components of the stack. It's open source. It follows an imitation-based methodology to provide rapid development and versatility, high simulation speed, and accurate simulation. And we integrated with 5 simulators. We created Virtual, which is a toolset encompassing multiple state-of-the-art techniques. And we validated against the high-end server-grade CPU, and we implemented 5 diverse use cases. You can find open source on GitHub. Yeah, and as I said before, it's very important, this type of work, because it can enable a common ground for researchers to implement their techniques and compare against. Thank you. I think let's have a quick break, 10 minutes, and we can continue with 2 more works. Am I audible? One minute. When did I stop? Plus 47, right?
So yeah,
Oh.
1 minute.
Yeah.
I can't help you here.
That's fine. Okay, let's continue. So, okay, simulation is nice, but we develop simulators so that we can evaluate our ideas, right? And now I'm gonna talk about two hardware operating synergistic schemes that try to accelerate the address translation process. And they both use the simulator that I just described. And these are namely Utopia and Revelator. Utopia was published in Micro 2023, and Revelator is one of our latest works, and it's currently under submission and uploaded on archive. So this is Utopia. This is a fast and efficient address translation via hybrid, restrictive, and flexible virtual to physical address mapping. So I'm going to explain what this complex title means, basically. I will not go again into the overheads of virtual memory and the background because I just gave it to you before. So we're going to just directly jump to the key idea of Utopia and how we improve address translation. Something that I didn't talk about. So a core feature of virtual memory management is that the mapping between the virtual to the physical pages is fully associative. And what does this mean? This means that on the left, we have the virtual address space. On the right, we have the physical address space. And this means that essentially, this specific virtual page can be mapped to any free, arbitrary physical page. And the operating system will decide where to put the virtual page based on availability. And what's the problem with this? This fully associative nature of the mapping creates a need for the page table, because we would always need to store a mapping between the virtual to the physical pages. And whenever we want to find where our data is, we need to perform the page table walk process. And the page table walk process works in the following way. Basically, we would need to access the first level, the second level, the third level, the fourth level in x86 systems to finally find out the physical frame number. So we need to perform 4 sequential memory accesses during a page table walk in x86-64 system, some of which will be very well filtered by the hardware components that we have, but they still end up we still end up spending too many cycles on performing the page table walks. So some recent works have proposed ideas on how we can restrict the virtual to physical address mapping to perform much faster address translation. What does that mean? So we have the virtual address space again, and we have the physical address space. And now we don't use a page table anymore. And what we want to do is we retrieve the virtual page number 00110 here. We pass this through a hash function. Essentially, we could use a hash mask, which means that I'm masking basically the last 2 bits. And then I am retrieving the final physical page number. So what is the benefit of this? The benefit is that I do not need a page table anymore. I could simply hash the virtual address. I could get back its location in the physical address space. The bad thing is that if I do this, then if data is already in this specific location in the physical memory because we had a hash collision, for example, then things might not go well. And we show here the drawbacks of restricting the virtual address, physical address mapping. If we do it across the whole physical memory, then we limit the core virtual memory functionalities, such as data sharing. So how would you share data if 2 virtual addresses from 2 different processes cannot be guaranteed in a guaranteed way mapped to the same physical locations? That's number 1. And second, we might increase the activity of swapping and accesses to the disk because we may not be able to map some virtual pages to physical pages if there are hash collisions. If we find out that this place is already reserved, then I need to store my data in the disk. I don't have another option. And here we show the effect of employing a restrictive mapping across the entire memory. And we observe that if we use only the restrictive mapping, this leads to a 2.37x higher swapping activity over the baseline. This means that we increase the amount of transactions we do from the disk because we cannot map many times our data inside the main memory because of hash collisions. So our goal in this work was to design a virtual to physical address mapping scheme that provides fast and efficient translation using a restrictive hash-based address mapping, while at the same time enjoys the benefits of the conventional, fully flexible address mapping. So the key idea of Utopia is to employ a new virtual to physical mapping scheme that enables both restrictive mappings and flexible mappings to harmoniously coexist in the system. And how does this happen? With two different segments. We employ some segments which are restrictive, which have a restrictive mapping, some other segments with a flexible mapping. So how does this look like? When we want to map our data into a restrictive segment, we take the virtual page number, we hash it, we find our location in the segment. And this offers much faster translation because we do not need to go through the page table, but it limits the virtual memory functionalities like data sharing and swapping. On the other hand, we have the flexible conventional segments. How do we map data inside these segments? We take the virtual page number, we go through the page table because data might be anywhere inside the segment, and we find out where is our data. This supports all conventional virtual memory features, but at the same time, this incurs high latency address translation. Let's see right now the properties of the segment that is restrictive. We're going to discuss two types of properties. First, how do we structure it? And second, which means how does the hash function look like, in a sense? And second, how do we perform translation for data that reside in the restrictive segment? About the structural properties, you can think of a RESSEG as an organization that follows the same principles of set associativity. You might know this from hardware caches or from hash maps, the concept of set associativity. And what does this mean? So we see here an example of a two-way associative RESSEG with two sets. So we organize the restrictive segment with 4 kilobyte pages. And the first two pages constitute the first set. And the next two pages represent the second set. And each set has two ways. For example, the first page corresponds to way 0 in set 0. What is good with that? Because we can basically tune the associativity of our design to have much higher flexibility and limit the amount of collisions we might have inside the restrictive segment. If we collide in the same set, we might place our data in a different way each time. We also employ in Utopia multiple RESSEGs in the system. For example, we might employ one RESSEG and one restrictive segment that uses 4 kilobyte pages only. We might use a restrictive segment that uses only 2 megabyte pages. And this way we can accelerate translation for pages that store both 4 kilobyte pages and translations that store only 2 megabyte pages. This also provides backwards compatibility with existing large page mechanisms that exist in the systems, right? So second, how do we do translation for data that reside inside such a segment? So again, so what's the question here? We have a virtual page, and the question is, how can I find out that the location of this virtual page inside this restrictive segment is here in way 0, set 0? How do I figure this out? So the answer is the following. We have two operations, the tag matching, which corresponds to what normal caches do as well, and set filtering. The tag matching requires comparing the tags of all ways with the tag of the virtual page. So to do this, we use a tag array that stores the tag of its entry. How does this look like? The virtual address is taken as an input. We pass it through a hash function and we determine two things, the tag and the set number. So we find the set number in the restrictive segment. After we find the set number, we figure out that, okay, the tag in the first way is the tag we want. And in this context, it matches But the question is, if the tag was not matching, would we always need to do the tag matching if, for example, the restrictive segment is empty? The answer is no, because we can filter out specific matches. How? We want to quickly discover essentially if a set in the restrictive segment is empty or not. If the whole set is empty, then I do not need to do the tag matching and compare all the tags, right? Because I know it's empty, there is no way my tag is there. So how do we do that? With an array of counters that keep track of the cardinality, essentially. They keep track of the number of pages inside each set. And we take again the virtual address, we hash it, we figure out the set number, and we have a bitmap here that says, okay, set 1 has some data, so you cannot skip the tag matching. But set 0 has some data, so you cannot skip the tag matching. But set 1 is empty, which means that if my virtual address is stored in the set 1, then I would not need to do tag matching. I know it's not there, basically. And then if the filtering is not successful, then I would need to do eventually the tag matching for my data. As a whole, how does address translation look like? This is an example with 2 restrictive segments, one for 4 kilobyte data, one for 2 megabyte data. And we're using one flexible segment in the system. So the rest of the memory is organized as a flexible segment. So when we miss in the L1 TLB, we need to perform 2 things at the same time. We need to perform restrictive segment walks, and the restrictive segment walk is figuring out, oh, is my data in the 4 kilobyte or the 2 megabyte segment? And at the same time, we do the L2 TLB access, and we parallelize these two so that we can get back latency. We can overlap these 2 operations so that we don't spend time sequentially waiting for each other. Once these are resolved, then we find out, okay, my data is not in the L2 TLB, my data is not in the restrictive segment for 4 kilobyte pages, and also not in the segment for 2 megabyte pages. This means that my data is somewhere in the flexible segment. And what is the way I figure out whether my data is in the flexible segment? Through the page table. So I need to do a page table walk, and this is the worst case scenario. There are three key challenges with these approaches. First, which data should we place in the restrictive segment? Like, how do I decide which data should I place in the restrictive segment? Second, how can I maintain the restrictive segments in the system? And third, how can I integrate Utopia in the address translation pipeline? How I can perform translation on the fly to figure out if data is in the restrictive segment for 4 kilobytes or not? Let's see how we place data in Utopia in the restrictive segments. So our goal is to place costly to translate pages inside the restrictive segment. And we propose 2 techniques to perform data placement in Utopia. First, a page fault-based allocation policy. And second, a page table tracking-based migration policy. What does the first one mean? It means that whenever I install the mapping and I decide that I want to allocate some pages, I will immediately put it inside the restrictive segment. And the second one means, if I made a mistake and this page is not so costly to translate, then probably I need to migrate it out of here or migrate it from the flexible segment inside the restrictive segment. How does this look like? So when we try to allocate a page, again, you can think of the minor page fault here scenario. We want to directly allocate the page inside the restrictive segment if the occupancy is low inside the restrictive segment. If this is the case, yes, we allocate it. If not, then we allocate it in the flexible segment. How can I check this occupancy very easily? Do I have a tag match or not in a restrictive segment? Are all the sets free? Is any of the ways in the set that corresponds to my data free or not? So that's how we figure out whether the threshold is larger than the occupancy. And again, the problem here is the following. I allocate my data there, but what if some piece of data cannot be allocated in the restrictive segment, but it's very costly to translate? So the answer is to use some unused bits from the page table to keep track of some counters that basically track the number and the cost of the page table walks for this piece of data. In other words, inside my page table, I store some counters in the unused bits that say, okay, for this piece of data, how many TLB misses did I have? How expensive was the page table walk that I did? How many DRAM accesses did I perform to access the page table for this piece of data? If this is larger than the threshold, then we migrate regardless of the occupancy in the restrictive segment. I might have a full restrictive segment, but the occupancy is not a concern here because I know that this piece of data is going to be very expensive to translate in the future. Second, how do we maintain restrictive segments in the system? We support, so OS supports Utopia in 3 ways. First, it can handle allocations in the restrictive segments. Second, replacements, which means that, okay, I need to replace some data from away. I need to evict it, for example, from the restrictive segment. Who does that? Who is responsible for doing that? The operating system through a replacement policy. And third, how do we handle migrations to and from a restrictive segment? Again, the operating system is the one responsible for handling migrations to and from the restrictive segment. The most interesting part, though, is this one, how we can integrate Utopia in the address translation pipeline. So we introduce a new hardware component called the restrictive segment walker, which enables address translation for pages that reside inside the restrictive segment. It has 3 components, basically. So it has an FSM that performs the tag matching and the set filtering, the operations I described before. And why is this good? Because this way we can avoid software-based accesses to translation structures. Second, we have very small caches for the tag array and the set filter. And why is this good? Because the accesses to the permission filter and the tag array may exhibit very high spatial and temporal locality because they're very small in size. We can fit them all inside the small caches. And third, we want minor modifications in the address translation pipeline. What do? We parallelize the restrictive segment walk, the discovery of whether a page is inside the restrictive segment or not, and the L2TLB access. Let's dive into more detail in these. So the restrictive segment walker has the FSM. The FSM generates the addresses for the tag array and the set filter based on the virtual address. So we take the virtual address, we hash it, and we find out where should I access the tags and where should I figure out whether this set is empty or not. So we first visit the caches, one for the tag array, and one for the set filter. These are the SRAM structures that store the most recently accessed tar and SF entries. If we miss in these 2, then we need to go through the cache hierarchy and the memory to be able to fetch these inside our components. So this is the workflow. We have an L1 TLB miss, right? Our data missed. We access the L1 TLB. We cannot find the translation there. And we have 2 parallel operations. First, the restrictive segment walk. So we first try to find out if our data resides in the restrictive segment or not. At the same time, we perform the access to the L2 TLB. So right now, we can parallelize this process and this process. If we miss in the L2 TLB, then we are waiting for the restrictive segment walker to tell us whether data reside in the restrictive segment or not before we start the very expensive flexible segment walk. And let's see 2 examples of how this is done. First, a page resides in a restrictive segment. And you can think of it this way. We have a flexible segment in the system, a restrictive segment, and we need to translate, we need to perform translation for this piece of data. We miss in the L1 TLB, and we start these 2 operations in parallel. So here we need to stall. So we cause a stall in the system because the L2 TLB is waiting for the restrictive segment walker to give an answer. Is the data there or not? So the data is actually in the restrictive segment in this scenario. So after stalling, I will abort the flexible segment walk. Why? Because I know the data is inside the restrictive segment. I do not need to do a flexible segment walk. Second scenario, the page resides in the flex seg. This is how the memory layout looks like in this scenario. And again, we miss in the L1 TLB. And here, the L2 TLB misses again. But the response we get back is that the data is not in the restrictive segment, which means that the TLB miss stall caused a stall. And then after the stall, we need to start the flexible segment walk. So we figured out that in the worst case scenario, we will pay for an extra stall for waiting for the restrictive segment walker to say, okay, my data is not here, so you can continue the process, basically. So this is what we pay. Someone could say here, why do I need to stall? I could simply do it while not waiting. I could start the flexible segment walk without waiting. Does anyone know what would be the problem? Not a problem, but what would be the disadvantage of doing that? What would be the disadvantage of not stalling and just starting at the same time the flexible segment walk as well as the restrictive segment walk? So what about power, for example? So you would need to pay a lot of power, right? In cases that your restricting segment walker always gives a positive answer, then you would basically start the flexible segment walk and you would spend a lot more energy, which is wasteful.
And how long is this restrictive segment walker in time compared to the flexible? How long
I have this in the paper, but this is around, like, I think, from 16 to 30 cycles, while the page table walk can last 150 cycles, 160 cycles. So the problem, though, is that you would send the requests to the memory hierarchy about the page table while you're performing this walk, and you would pay extra power and energy for something that is in most cases not useful, is useless. So that's the problem with this sort of approach. But it's a trade-off at the end, because if the restrictive segment walker is negative in its responses, then it makes sense to parallelize it from a performance point of view. The third and the easiest example here is a TLB hit. It doesn't matter where data reside. If we have a TLB hit at DL1, we don't need to do any of this. We find our data and everyone's happy. We abort everything. Our data is in the TLB. We can deliver the translation very fast without any overheads. With respective evaluation results, we evaluated with Virtuoso, and we executed workloads for 500 million instructions from the Graph Big Benchmark Suite, HPCC, XSBench, DLRM, and the Genomics bench. And we find out that we used as a baseline the Radix-based page table with transparent huge pages enabled. This means we used both 4 kilobyte and 2 megabyte pages. We used POM TLB, it's a software-based managed TLB. The state-of-the-art page table design in the literature, an approach that was discussed before uses contiguity, virtual to physical address contiguity, and Utopia. And we also compared against a scheme that uses a perfect TLB. Basically, this means that everything comes for free when it comes to translation. We always hit in the TLB magically. And that's how the performance results look like. This is the speed up over the baseline system of all these configurations. As you can see, here, Utopia outperforms the second best performing scheme, which is the contiguity-based one, by 13%, and the baseline Radix by 24%. Also, another interesting result, the performance of Utopia is within 95% of the perfect TLB. And when it comes to translation latency, I think this goes back to your question. So we can reduce the translation latency by 63% compared to the baseline system and 14% compared to the second best performing scheme. Remember the memory interference that we discussed before with the page table entries and the data. And here we plot the normalized DRAM row buffer conflicts. How many times do I need to change the contents of the row buffer? And as you can see, Utopia reduces the row buffer conflicts by 20% over the baseline system and 9% less than the perfect TLB that doesn't access any sort of page table data. There are more results and details in the paper, like as we discussed, like the sensitivity to parallel and serial TLB access, sensitivity to the restrictive segment size, the reuse level distribution for 4 kilobyte pages, and a lot more. In conclusion, we propose Utopia, a new virtual to physical mapping scheme that enables both restrictive mappings and flexible mappings to harmoniously coexist in the system. Utopia achieves 13% higher performance than the state-of-the-art contiguity-aware translation scheme and 95% of the performance of an ideal perfect TLB. And it's open source, you can find it. It's also implemented in Virtuoso. It's very easy to run it. Any questions on Utopia? Can anyone find any disadvantage? Because the next work that I'm going to discuss.
So the evaluation.
Do you have a mic? Yeah, it does.
So the question is, the evaluation that was done are there any results for mixed workload setting, like running multiple workloads on the same system, which are equally performant or require equal compute?
I don't remember if we have multi-programmed results in the paper. I don't remember. Yeah, I think yes, we had multi-programmed results in the paper. Not equal, but like it's a random mix of workloads running at the same time and sharing a segment, basically.
Okay.
So you can have multiple workloads, which basically they share all the segments, share the same segment.
Okay. Okay. And is the portion that is made rest seg and the flexible seg, is it can it be made flexible? Like with runtime,
Okay.
can we change the portion? Because when there is less workloads running, we can have more portion to as rest seg.
Yeah, that's a good question. So right now we set it for the purpose of this work. We set it statically. So when you boot, you have a large segment, which means 8 gigabytes, 16 gigabytes, or something related, some portion of your memory. Of course, one research area would be how do I make this, how do I basically this elastic? I totally agree with that. But in general, that's a hard problem because I would need to allocate contiguous memory, that's one. And then when something relies on hashing and you want to migrate it to a larger one or a smaller one, it changes the location of the hashes, unless you use a special form of hashing, which I don't have time to discuss right now, where you can avoid this problem.
Okay. Yeah.
But I agree, yeah, it's a good thing if someone can basically make it a lot more elastic. Parenthesis to that is that like your segment might be very large, right? But the page table, one optimization that we could have tried to do, but we thought of it later, was that you can treat still the restrictive segment as part of the flexible one, which means that if the page table wants to, if the flexible segment, if the operating system wants to place something inside your restrictive segment, then it can by using the page table, and it can update the structure so that you don't access it, right? This is to avoid the underutilization problem of the restrictive segment, basically. Anything else? Okay, this is one of our latest works. I agree. The elastic part was a bit problematic. And another problem is that we figured out is that like the cost of in systems, for example, where you need to migrate, right, from the flexible segment to the restrictive segment, the cost of migrations sometimes is unbearable. So if, for example, your heuristic does not work well with respect to what you need to migrate, then you might fall into energy and QoS problems just because you're doing lots of migrations. And in general, migrations are not nice. So doing migrations is problematic in modern systems, basically. So that's why we came up with a sort of a different approach to use this sort of hashing. And I'm going to talk about Revelator on how we can perform very quick data fetching via hardware-esque cooperative speculative address translation. So the motivation is the following. We can basically, in modern systems, predict the physical address to start fetching data early. So what does this mean? We have our virtual address here, and we need to perform address translation, which, it's very slow. So we can only access our data only after translation is done and the physical address is available. But what we could do is the following. We could take the virtual address. We could speculate about the potential physical address that our data resides into. We could start fetching our data based on this hypothetical speculative physical address. And then when the translation result, we would have already fetched our data inside the cache hierarchy, for example. So we would not need to wait for data to be accessed from the main memory anymore, because they would have already traveled inside the memory hierarchy. This means that we save cycles because of this process. What is the problem, though? How can we predict the physical address? First, because the page location heavily depends on many factors, like current system state. For example, how does the fragmentation look like? How many users have used this machine? How long is this machine up for? Second, allocation order. If I change the way I allocate my virtual addresses, then where they are stored in the physical memory changes. And we have verified all this with experiments in the paper. Third, other co-running applications. If I run 5 applications at the same time, then the order of allocation changes, basically. And fourth, the large page allocation policy. If I use large pages, then I do not have the guarantees that, again, I'm going to use this piece of physical memory or another piece of physical memory, because it might defragment memory, it might compact memory together. So predicting the physical address is very, very, very challenging, as page allocation is heavily dependent on many different system-level factors. So for this work, imagine I created the Bicron benchmark, and we run under all these stress points that I discussed before, and basically the matches in virtual address to physical address pairs was literally 0. So you cannot match in any 2 consecutive runs any virtual address to physical address pair. So our goal in this work is to effectively predict the physical address while being oblivious to the system state and conditions, with minimal changes to the operating system and with minimal changes to the core architecture, and without affecting correctness. So I just take the physical address and I speculate without affecting the correctness of the program. So, and thus we present Revelator. The idea is to co-design the hardware and the operating system to perform highly accurate speculative translation obliviously to the system conditions and state. So how does this work? At the operating system side, we take a virtual page number, and guess what? We hash it. And after we hash it using one hash function, and we see that the page is occupied, I cannot place it there, I try out with a second hash function. And I'm saying, okay, maybe I will place the data there. And in this scenario, the hash-based allocation, what does it do essentially? It limits the potential physical address, physical page locations. So if I use three hash functions to do the data placement, I restrict the potential locations of my virtual page number to 3 or more, but I will discuss this later. So why does this help? Because I can inform hardware that, okay, the operating system always tries to allocate data using a hash function. So be aware of it so that you can make nice and correct speculative decisions about it. So what happens is that whenever right now we want to perform address translation, we take the virtual page number and we compute on the fly these 1, 2, 3, 4 hash functions, and we send over data that are accessed speculatively so that we overlap the latency of performing the translation. We still pay for the latency of the translation, but at the same time, we start fetching our data much, much earlier in the pipeline. And this is why we can save cycles, yes.
So we fetch all of that simultaneously?
Yes, but not exactly. Basically, I'm not sure if I have it in the slide since I wanted to simplify it, but we use a filter for this. We use the filter so that we fetch only the ones that we can afford. So if you send 5 requests in parallel for every translation that's missing, let's say in the L2 TLB, then essentially you're going to waste too much bandwidth, right? So if you observe that your bandwidth usage is very low, if your bandwidth contention is very high, then you need to restrict this. But you can use a proxy to figure out how many functions you're going to use. And the proxy is the following. The proxy is, how many allocations have I done with hash function 1? 60%. So I'm going to only use hash function 1. How many allocations have I done with hash function 2? And so goes on. So we're using the bandwidth contention and the number of allocations you're doing with each hash to figure out how many of these are we going to ship to the memory hierarchy to avoid the bandwidth contention problem. I think, I'm not sure what I described in the slides, I don't remember it, but we can discuss it later as well. So how does the page allocation algorithm look like? So we take a virtual page, we hash it, and we find out that this page is free. So this means that with the first hash function, I was able to place my data inside the physical memory. However, the bad scenario is that the page is not free. I have a hash collision, basically. So I hash again. I change the hash key, potentially. And I end up in a different physical page number. And I do this n times. And the n we tried in the paper is from 1 to 6, if I remember correctly, or 1 to 5. If we end up not being able to place our data with n tries, then we fall back to the conventional mechanism. And we're like, okay, I cannot place my data with a hash function because I had 5, 6 collisions. So I would place my data wherever the OS allocator finds a free page, which means that if I speculate for this piece of data, I'm going to make a mistake because it's not allocated using a hash function in the physical memory. So what is the key here? That the key idea of this work is that the OS allocation algorithm, which means the hash function list, the hash choice pattern, is driving basically the speculation pattern that I'm following at the hardware level. So the key benefits is that we have minimal changes to the hardware, which means we only need a finite state machine to perform the physical address speculation. Essentially, we need a hash function circuitry that generates the hashes based on the virtual page number. Registers to select the OS chosen hash functions. For example, if the operating system decides to change the order at which it allocates with hash functions, then we can propagate this to the hardware so that the hardware is aware of it as well. And we want minimal changes to the operating system. We basically prototyped it in a real Linux system, and we find out that the body allocator simply tries the hash-based allocation before falling back to the conventional allocation. This offers basically operating system-driven, highly predictable allocation. Again, we evaluated this with Virtuoso, and we had 11 comparison points. As I discussed, this enabled us to basically have a very wide variety of comparison points against this scheme. So you can see all of them here. I'm not going to describe them. You can see the speed up over transparent huge pages, which means that I am accelerating over a system that's using both 4 kilobyte and 2 megabyte pages. And we saw 15% higher performance in a heavily fragmented system compared to the second best performing scheme. What does this mean? If memory is heavily fragmented, which means that I do not have many 2 megabyte pages to give, which lowers the reach of my TLBs, then I can perform a lot better with Revelator because Revelator is not affected by this sort of fragmentation, but rather exploits it by allocating with hashes, which essentially create more and more fragmentation in the system. You can find more details in the paper. And yes, the work is still under submission, so I will not provide more details. Any questions?
See Utopia and Revelator working synergistically. Do you see Utopia and Revelator working together synergistically? Because the concept of ResSeg and flexible seg is, can probably be combined with the speculative address translation over here.
There is potential for a synergistic scheme. I just feel that the way Revelator is designed is a lot more simpler, achieving similar type of results. From an energy, if we think it only from, let's say, energy's point of view, Utopia does not spend a lot of energy on translation because we can quickly figure out if data is in a restrictive segment or not without performing the page table walk. So if we take energy into account, Utopia is better because the restrictive segment walk is a lot faster than the page table walk and it consumes less energy. If we think of it only from the performance's point of view, Revelator in a system, for example, with very high bandwidth, right? Then it can perform potentially better than Utopia because you're not restricted by the size of the restrictive segment, right? So I think there are cases when it comes to energy where Utopia works better than Revelator, and cases when it comes to performance where you just care about performance, bandwidth is high, your bandwidth channel is high, capacity is high, and then you can issue many prefetches with Revelator and get most of performance back. I think Revelator is a more, like our motivation was to design Revelator as a simpler version of Utopia that does not require, that gets most of its benefits without requiring many changes in hardware and many changes in the operating system. Like it's sort of an alternative to Utopia. It's not, it doesn't completely remove it from the game. Okay, I think if no one else has questions, I think we will wrap up for today, because the next paper will take me another 30 minutes and I don't want to waste your time and overflow after 6. Anyone else? Of course, if anyone is interested, we can discuss about, like, if you want to do a thesis with us, do research on the topic, feel free to approach us. Yes.
Does this create any security threats? I mean, predictability in real memory is kind of a potential threat.
This is a reviewer's question, basically, what you just said. So based on our analysis, it doesn't create any new security threat compared to the existing threats. So what does this mean? In Revelator, you speculatively fetch data, right? But you only use the piece of data that is the correct one. So most attacks like Meltdown, Spectre, if you have seen this piece of attacks that rely on speculation, they fetch speculatively some data and perform some sort of computation on top of them. That's not the case with Revelator, because we just speculate about what might be the data that will be fetched next. And if you find it in the caches, that's perfect, because you reduce the amount of time you spend on fetching them. If you don't find them in the caches, you might have fetched a different piece of data, which is useless and nobody used. So you simply consume and waste bandwidth. So from a security's point of view, yes, there might be some very sophisticated attacks you could do to figure out a pattern of allocations, let's say, which could break very advanced defenses in operating systems like address layout space randomization. But there are techniques which we describe in the paper that can stop even this piece of attack. But yeah, when it comes to the speculation-based attacks, given that we do not, in Revelator, we do not use data that we fetch if they're not correctly fetched, then they do not, I think they do not open any new avenues for speculation-based attacks. Yeah.
So, is there any main memory interference study that you did with Revelator similar to Utopia?
I think we did, yes. We did one specific study where we show how we affect the main memory contention in a mechanism with Revelator that performs filtering of requests versus a mechanism with Revelator that does not perform filtering versus the baseline system. And we saw that, like, if you employ a sophisticated filtering, you do not cause a very high consumption in memory bandwidth, even in systems where you do wrong speculations. We have a plot in the paper, I think. I can send you the plot, the paper, basically.
And what about row buffer swaps?
About you mean conflicts, right?
Yeah.
We cause more conflicts. I remember this.
Okay.
So I do not remember the amount exactly, but naturally, if you're sending a lot more requests to the memory hierarchy, you're gonna perform a lot more conflicts. But because of the fact that we gain back a lot of translation cycles, we end up not wasting more energy for this piece of conflicts.
Okay, thank you.
Okay. Thanks, everyone.